Okay, today we are going to learn matrix operations. So for a matrix operation, first we need to understand what matrix is. The matrix is an array of numbers arranged in rows and columns. For instance, some of the numbers 3, 2, 1, -4, -5, 0. So you can see this number, they are arranging in 2 rows and 3 columns, and we put that in the bracket. And most of the time matrices we like to use the capital letter to indicate a matrix. And this matrix we have 2 rows, right? You have those are the row and those are the column. Okay, so this is 2 by 3. This is indicating the row number or number of rows, and this number is indicating the number of columns. Okay. So the whole thing we call that is the order. Okay, this is we call that is the order of a matrix. So which means if we have matrix A is m by n, okay, that means m rows and n columns. Each of the entries we call that is entries the matrix of the elements of the matrix, and each element we have that location for that. For instance, for this matrix also we can indicate it with A, I, J. Right, so this is the elements of the matrix, and I, it means I row, and J, that means J column. For our problems in here, if I want to see, oh, what is the number A12? That means the elements located at the first row and second column. We take a look at the numbers. First row, second column. So this number will be 2. If you're looking for 2, 1, that will be completely different. That means what is the element in the second row and first column. Going back to the matrix, take a look. Alright, second row, first column, so the A21 is equal to -4. When I talk about the two matrices are equal to each other, we need to make sure the order of these two matrices must be agreed or the same. So if A equals to B, if and only if their orders the same order. Let's say m by n. And the corresponding elements must be equal to each other for all the elements. For instance, I still use the A matrix as above, and if I say A matrix is 3, 2, 1, -4, -5, 0, and I know another matrix B have the element is x, y, 1, maybe -4, A, B, to find all the unknown, right? So this one is corresponding to this one, y corresponding to 2, 1 corresponding to 1, etc. So from here, we know that the x must be 3 and y must be equal to 2 and a must be equal to -5 and b equal to 0 because they are the corresponding elements. Now, so far now we can work on what is the addition, how to add or subtract the matrices. Use another piece of paper here. When you add or subtract the matrices, not all the matrices can be add or subtract with each other. We have certain condition in there. And first is these two matrices must be the same orders. Okay? Let's say that A is the matrix with some element inside, and B is the matrix as well. They all have the order of m by n. Okay, when we add them, if we have A plus B, what you should add is adding the corresponding elements. Okay, so we result still is m by n matrix. And when you subtract, similar idea, you subtract the corresponding elements in here. Let's see. For instance, I'm going to have a matrix A is defined as 2 by 2 matrix. Okay. And B also is a 2 by 2 matrix. So they are both the same dimension or same order. This kind of matrix, we call that a square matrix. So when you have the same number of the row and some number of the column, the matrix is a square matrix. And going back to our problem, I'm going to see if I can perform the addition between these two matrices. The way we add them is we are adding the corresponding elements. So original is 2 by 2, so result is still 2 by 2. Okay, when you see a 2 by 2 matrix, you have 2 rows and 2 columns. Right? So for each of them, how to find this? First one, first row, first column, first row, first column. We're going to add these two numbers together. First row, second column, plus first row, second column from B matrix. Similarly, for this one, it's 3 plus 0, and this 5 plus 4. Simplify that. So that was 0, 4, 3, 9. Subtract. Okay, A subtract B. So you just find the corresponding matrix elements and perform the subtraction. 1 minus -1, -2 minus 6, 3 minus 0, 5 minus 4. Simplify them. So that's 2, -8, 3, 1. All right. Some special matrix. 0 matrix. 0 matrix means the matrix have all the elements are 0. For instance, if we have a 0 matrix is 2 by 2, so 0, 0, 0, right? So they have all the elements are 0. Just like the real number, for matrices, we also have the additive identity. For the real number 0 is the additive identity, and in the matrices is, so the m by n 0 matrix is additive identity for m by n matrix, because any matrix adding its corresponding additive identity will be equal to the matrix itself. In the real number, we have the additive inverse, which is the opposite of the number, and for matrices we have that similar idea as well. So for any matrix A, the additive identity, additive inverse of A is negative A. For instance, just use my example in here above. If A is 1, 3, negative 5, okay, negative A will be all the opposite of each element, so will be negative 1, 2, negative 3, and negative 5. Okay, recall the real number. When you're adding a number where it is additive inverse, then the result should be 0, right? So in our case, the same way, if you have A plus 1, negative A, if we perform addition in here, and you will see we also result as the 0 matrix, which is the additive identity. Okay, so the properties in the real number, it also work for our matrices. Okay, let me see. There's some of the property of the matrix additions. Again, let me clarify some of the notation. A, B, C are m by n matrices, and this is not number 0. This is 0 is a matrix. So the following properties, they are all true. For addition of the matrices, we also have the commutative property. Which is we can switch the order of the additions. And for matrices, we also have the associative property, which is we can regroup the matrices when we add them. And also, when you have a matrix adding the 0 matrix, remember this is not a number 0, it's a 0 matrix. It's equal to matrix itself. So the additive identity property also true in the matrices. In the real number, if we add two opposites, we will get 0, right? So for matrix, similarly, if we add a matrix which is additive inverse, then we will get a 0 matrix. Remember, this is a 0 matrix, it's not the number. Okay. All right. Now we talk about addition, subtraction. Let's see, do we have multiplication for matrices? Yes, we do. Multiplication, we have two kinds. One kind is scalar multiplication. The real number or the constant we talked about in the past, in here we call that is scalar. Okay. So if you have A is a matrix, and let's say C is a scalar, which is a number, then when you use this scalar multiply by a matrix, indeed you can use this scalar multiply every single element inside the matrix. What I meant in here is let's take a look at this simple example first. If I have a matrix A is equal to, let's say, 2, -3, 5, 6, 1, 7. All right. And I'm going to find what 2A is, right? So you have 2 times this matrix, 2, -3, 5, 6, 1, 7. The way it works is you use these 2 multiply every single element inside this matrix. By the way, this matrix is 3 by 2 matrix. So we find that by using 2 times 2, 2 times -3, 2 times 5, 2 times 6, 2 times 1, 2 times 7, and simplify that, that will be 4, -6, 10, 12, 2, 14. Okay, how about some combinations? For instance, and I said, okay, I have matrix B is equal to -1, 4, 3, 0, and I have matrix D is equal to 3, 7, 5, -1 here. And I'm going to find 3A minus 5, 3, my mistake, 3B minus 5D. Let's see how to perform that. Can we perform this? This is 2 by 2, 2 by 2. When we subtract, the matrix should be the same order. They're the same. So we should be able to do so. First order operation, I need to use the scalar 3 times matrix B. And subtract 5 times matrix D. When we perform the scalar multiplication, you multiply the scalar inside the matrices, every single element need to multiply by the same scalar. Right? 3 times -1, -3, 3 times 4, 12, 3 times 3, 9, 3 times 0, 0, minus, I'm going to use 5 times 3, 15, 5 times 7, 35, 5 times 5, 25, 5 times -1, -5. That going back to subtraction between two matrices, we subtract the corresponding element, -3 minus 15, -18, 12 minus 35, -23, 9 minus 25, -16, 0 minus -5, +5. Right, so that is the scalar multiplications. What kind of properties does the scalar multiplication have? Basically, the properties for the real number multiplications, it will apply in here as well. Okay. If A and B are m by n matrices, C and D are scalar. So let's take a look what kind of property we have in the real number. The real number, we said that we have this associated property, right? If you have two constant or scalar multiplied together, multiplied by a matrix, then you can just multiply one scalar at a time. It works too. So this is the associated property of scalar multiplications. And how about we have, if we have a 1, number 1 times A is still matrix A. Okay, so this is scalar identity. We also have the distributive property in matrix as well. If you use a scalar times a sum, also apply for the difference as well. Of two matrices, you can use this scalar multiply each matrices and then sum that. It will work. And also it will for if you sum two scalar and then multiply by matrix, you can use each the matrix multiplied by each of scalar and add them together. So this is distributive property also apply for the scalar multiplications. Right. Let's see how we can use that in solving equations. Let's move on to matrix equations. If we take a look of the name matrix equation, yeah, you have an equation and then you will have a matrix or some matrices. You just saw that just like you showing the real numbers equations. For instance, let me start it from an example. Yeah, given A is equal to 1, -5, 0, 2, and B also is given as -6, 9, 5, 1, and we are going to solve for x, which is having 2x plus A equals B. Let's just ignore these matrices. If you see an equation like this, how can we solve this equation? First step, we will subtract A from both sides, right? And we have 2x is equal to B minus A. And then we say, okay, we are going to multiply the 1/2 on both sides of the equation, or you're thinking divide by 2, like this. Then we have x equal to 1/2 of B minus A. So let's see what B and A are. In this problem, it is given B is a matrix -6, 5, 9, 1, and A is 1, -5, 0, 2. Well, these two matrices have 2 by 2, same dimension. Then we can perform the subtraction between them. The half, subtract the corresponding element, -6 minus 1, that will give us -7. 5 minus -5, that will give us 10. 9 minus 0, that's 9. 1 minus 2, that's -1. And this is a scalar multiplication because we use the scalar 1/2 multiplied by this matrix. Distribute the 1/2 inside. 1/2 has -7, -7/2. This is 9/2. This is 5, -1/2. The same as the other equations. When you find a solution, we are better to check our solution to see if it's correct or not. By substituting this matrix we found back to the original equation, let's check. 2x plus a was 2x. 2x, x is this one we found, plus a is 1, -5, 0, 2. This one will be -7, 10, 9, -1, plus 1, -5, 0, 2. Alright, a little bit out of space. Let me move the paper up a little bit. That's equal to -6 and 5 and 9, 1. Let's see, is that the same as B or not? Let me get that back very quick. -6, 5, 9, 1. Yes, it is equal to B. Then the solution is correct. Therefore, the X is equal to, is a 2 by 2 matrix with element -7/2, 5, 9/2, -1/2. So we see we can apply all the addition, subtraction, and scalar multiplication inside this equation and solve for the unknown matrices. Well, how about if we can multiply matrices and matrices? Not always, depends. We have certain conditions we need to follow. Okay. Let's take a look from a simple one, like say 2 by 2 matrix and maybe 3 by 3 matrix, how to multiply those matrices. If we have a matrix A times B, okay, that's an order for A, that's a requirement order for B. The first matrix, for instance, is M by N, and this one M by P matrix. So when you multiply the two matrices, the inner dimension must be the same. So this one must be equal. Okay. What I meant in here is the number of the columns in the first matrix must be equals to the number of the rows in the second matrix. If this condition do not agree, then we cannot multiply the two matrices together. The way we are going to multiply is, for instance, if your A matrix is, this is a matrix A, is an M by N matrix. and you multiply. I'm going to use a little bit different size in here. Maybe this is matrix B is M by P matrix. The way we are going to multiply is you are going to result a new matrix with new dimension, and the new dimension is forming by the same number of the rows of the first matrix. So we are keeping the same number of the rows and same number of columns in the second matrix. So your product of the matrix will be keeping the outer dimension, which is M by P. The way we multiply is we are going to, for instance, I have an element in here somewhere, P, I, J is the product element in here. So this ij, you will select the I row from the A matrix and multiply the J column, maybe somewhere right here, the J column from the second matrix. We are going to multiply them. I know you might be a little bit confused what I'm talking about right now. Let's take a look of several examples. We are multiplying. Let's just start it with an example as maybe 2 by 2 matrix. Then I have a matrix 3, 2, 1, 5 multiplied by 10, 7, -1, 0. Okay, let's see. First, you need to check if they can be multiplied or not. This 2 by 2, this 2 by 2. Yes, the inner one that agree to each other, right? So the product that will be equals to the outer one is telling us what the product is. Let me get some space in here because I'm going to show it to you how to multiply them together. So in this product, we have 2 rows and 2 columns. The way we are going to multiply is, think about this is first row, first column. So we are going to use the first row from the first matrix times the first column in the second matrix. So first row locating here, then you multiply the corresponding one. So it's 3 corresponding 1, first one times first one, and add second element times second element in the first column in here, 2 times -1. How about this one? So this one you can see it is first row, second column. So I'm still using first row, but multiplied by second column element. So 3 times 7 plus 2 times 0. Right here. Right. This one is second row, first column, and I'm going to use second row for first column element. First times first, second times second, so 1 times 10 plus 5 times -1. This is second row, second column, so second row, second column, 1 times 7 plus 5 times 0. Okay. Then we simplify all the additions. 30 minus 2, that is 28. 21 plus 0, that's 21. 10 minus 5, that's 5. 7 plus 0, that's 7. That's how we multiply the 2 matrices right here. And how about not square matrix multiply? Oh, let me go backward a little bit. So if I say this is A, B, okay, let me do BA. B times A, so that will be 10, 7, negative 1, 0. A, that is 3, 2, 1, 5. Applying the similar idea. 2 by 2, 2 by 2, so my product is still 2 by 2 matrix. And again, first row, first column. So first row coming from the first matrix, first column come from the second matrix. So 10 times 3 plus 7 times 1. That's this one. First row, second column, first row, second column. So 10 times 2 plus 7 times 5. First row, second row, first column, negative 1 times 3 plus 0 times 1. Second row, second column, negative 1 times 2 plus 0 times 5. Simplify that. And that will give us 30 plus 7, 37. 20 plus 35, that will be 55. Negative 3 plus 0, negative 3. Negative 1 plus 0, negative 2 plus 0, negative 2. Now compare these two matrices. They're not the same. Interesting, right? So for the matrix, the commutative property is really not exist, because you cannot A times B is not equal to B times A. Yeah, it's a little bit harder to believe that, but that's how it works in matrix. Let's take a look at another example. I'm going to stop. Okay, I need to stop calling them A and B. Let's call this one C is equal to 1, 2, 3, just using some simple number. And D is 4, 5, 6. Those are very special matrices. This you can see only have row, right? So we can, sometimes we call this as row vector. Or single row matrix. And this is column vector, because we only have single column. Let's see if we can multiply them together. If we take a look, C is 1 row, 3 columns, so it's 1 by 3. And D is 1, 2, 3, 3 row, only single column is 3 by 1 matrix. Let's see if I can do the multiplication C times D or not. So C, D. CD, let's see, C is 1, 2, 3, and D is 4, 5, 6. Again, this is 1 by 3, this is 3 by 1, and we check the inner dimensions. So this is inner 3 and 3, they agree. Yes, we can multiply together. And the result will be 1 by 1. So the result, it will be still a matrix, but only have 1 row and 1 column. Multiply that. First row times first column, right? So row 1 times 4 plus 2 times 5. Second element times second element plus 3 times 6. That is equal to 4 plus 10, 14. 14 plus 18, that's 32. So it's a 1 by 1 matrix. How about I switch them? D times C, is that possible? So D is 4, 5, 6, 1, 2, 3. Again, this is 3 by 1, and this is 1 by 3. If we check the inner dimensions, these two, they are the same. Yes, I can multiply, and my result will be the outer one, 3, 3. So it's 3 by 3. So that is the new matrix we are going to get is a 3 by 3 matrix. Let me write a bigger space because we are going to do the operation in between. So that is 3 row, 3 column. So I need to fill out all the information. The first one is first row, first column. First row, first column. Oh, only one element. Multiply together. First row, second column. So it's 4 times 2. First row, third column. 4 times 3. Second row, first column, second column, third column, so on. So 5 times 1, 5 times 2, 5 times 3. And this one 6 times 1, 6 times 2, 6 times 3. Let's see, let me remove this one. Alright, let's simplify those. Number, first row 4, 8, 12, 5, 10, 13 is the second row. The third row 6, 12, and 18. That's 3 by 3. Let's see another one. Now we just need to see a lot of example to get some idea for that. Let's see. If I have matrix E is equal to 1, 2, 3, 4, 0, 2, negative 1, 6, and matrix F is equal to 4, 2, 1, 3. Okay, let's do the multiplication again. E times F. Okay, again, this is 2 row, 4 column, and this is 2 by 2. Okay, so if you use the E times F, well, that's an issue. E is 2 by 4, F is 2 by 2. The issue is this number and this number not equal. So this multiplication cannot be performed. Okay, so this is impossible to perform. You can see that not all the matrices can multiply together. How about F times E? F is 2 by 2 again. E is 2 by 4. Oh, these two are agree. Yes, I can multiply. So that will be F is 4, 1, 2, 3. And E is 1, 2, 3, 4, 0, 2, negative 1, 6. So the result will be 2 by 4. So we have 2 row and 4 column. Need to figure out. It's 2 row and 4 column. First row, first column, so it's 4 times 1 plus 2 times 0. First row, second column, 4 times 2 plus 2 times 2. First row, third column, 4 times 3 plus 2 times negative 1. And 4 times 4 plus 2 times 6 is the first row, third, 4 column. Similarly, we are going to do the second row. 1 times 1 plus 3 times 0. 1 times 2 plus 3 times 2. 1 times 3 plus 3 times negative 1. And 1 times 4 plus 3 times 6. Simplify them. So that one is 4, and this is 8. 8 plus 4, that's 12. 12 minus 2, that's 10. 16 plus 12, that's 28. And this is 1, that is 2 plus 6 is 8. 3 minus 3 is 0. 4 plus 18, that's 22. So we can get this is the result. Right, let me go over what we just did in here for the matrix multiplication. What kind of properties will be held for the matrix multiplication? For matrix multiplication, the associated property still exists, which is you can regroup them as long as you don't change the order. Okay, left hand side still left hand side, right hand side still right hand side. But the commutative property doesn't exist for the matrix multiplication. We have the distributive property for matrix multiplication as well. So you can distribute the matrix A inside the parentheses A times B plus A times C. Or the other way, if we have sum times C, that will be A times C plus B times C. Make sure you don't switch the order. Or you have, if we have an scalar, right, times the matrix product, make sure don't multiply each of them separately. You can use this scalar times the first matrix and then multiply the second matrix. So those are the property of the matrices. All right. We are going to stop in here. Hopefully next time we can come back to visit more example of the matrix multiplications. See you next time.